Hey guys, so this is a problem from chapter 2, problem number 22 from electromagnetics with Chang. So you're given a vector function A, and your goal is to verify the divergence theorem for a cylindrical region with r equals 5, it's equals 0, and z equals 4. So we have r equals 5, and then we go from z equals 0 to z equals 4. I am going to, so here's the equation just for the general divergence theorem. So it's flux across the surface. So every surface, so the top, the side, and the bottom, the flux that's coming out perpendicular to those surfaces. So perpendicular to the top would be straight up. Perpendicular to the sides would be, it's kind of coming out radially, so every radial direction. So it's in the r hat direction for perpendicular to the side, and then perpendicular to the bottom would be coming straight down in the negative z hat direction. So those are our ds vectors. What these are going to be, we're going to have a ds for the top, a ds for the bottom, and a ds for the walls. So it'll be a differential surface so an equation to calculate that the value of that surface area, and then a vector that will point straight out of the surface that we're going to be able to use to determine the flux through that surface. So before I get into the problem, I am going to do a little bit of background about setup for why we're setting things up this way, and then I'm going to do a little bit of background for where these ds values come from. If you want to skip this, please feel free to fast forward to when I start on the second page with actually solving the problem. So feel free to skip ahead now. All right, so a little bit about the general setup. So for the cylindrical coordinate systems, the reason why we know that we can center our cylinders at z is because when we set up our coordinate system, our r is always going to be in the r hat direction. Same for if we have a spherical vector, like A would be some sort of a spherical coordinate system vector. When you have this r value, you line up your r hat along, or your r along the direction of an r hat. So whenever you have a cylindrical or a spherical coordinate system, when you're setting up your coordinate system, it is with respect to these r values. So that's why we know that we can kind of center this cylinder. Somebody asked me that question, and I thought it was actually very, it was something I thought was good to touch on. Okay, so a little bit of a background for ds and dv for our surfaces. So these are just general equations for your ds for just like a circle, ds for the walls of a cylinder, and then dv for a cylinder. These are general equations. You can go ahead and use them anytime you have a cylindrical shape, or in this case, for this one, anytime you have a flat circle and you're trying to find a ds coming out of that circle. The only thing that might change is this vector direction. It might be like negative z, but you can use this kind of general expression here for the differential surface area, because it's the differential surface area of a circle. So looking at the equations that you know very well, here's the equation for the surface area of the circle, and we can see that if we reverse engineer it here, we can actually break it apart and see how we're getting that ds expression that we use to get our vector ds. The reason why this is not a vector and this one is a vector is that our vector ds just has the z hat direction, whereas our ds here is just the magnitude here. So that's also laid out over here for the walls of the cylinder. So you can see this is just the general equation for the surface area of a cylinder. And from that surface area, we can break it down and see where these components are coming from. So when we turn it into this dphi value, when we're saying 0 to 2 pi, what we mean is we go back and look at our shape. So this phi, when we set up our cylinder, this phi direction will always be the same as phi, is actually going around the space of our circle. So when we have 2 pi, what we're saying is that this phi angle is actually going all the way around. So we have a full cylinder. If we had a half of a cylinder, for example, I was hoping that would snap there. For example, we cut this shape in half, and we only were dealing with like a half cylinder here. Our phi would go from 0 to pi. So these bounds are important when we're kind of setting up our equations, because when we evaluate these, we may find that our shapes have different bounds, if they're quarter cylinders, half cylinders, or if they're some other configuration. And these bounds are going to be important, especially when we're dotting things with our force vectors. It'll change some of these components. So these base differential surfaces are important to work with and kind of understand, but that's why we're decomposing them, and we can't just use these general equations for surface area. because there's some variability in terms of the shape, or some variability in terms of the actual variables in our vector. This one is for a differential volume. So again, kind of the same concept. As we deconstruct it, we can break it into these vector directions. This is just a general, this would represent like a general cylinder with a height of from 0 to z, an angle, so height from 0 to z, an angle from 0 to 2 pi, so an angle from 0 to 2 pi, and a radius from 0 to r. So it's just a little bit of background. If you don't have to derive these, obviously, from the surface area equations. Anytime you have a flat circle, you can use the differential surface area for a circle. Anytime you have the wall of a cylinder, you can use a differential surface area for a cylinder. Just pay attention to these vector directions and make sure that they line up with the problem that you're trying to approach. So make sure to check your figure and make sure that that works out. The differential volume you can use anytime you have a cylinder as well. Okay, so moving on to solving the actual problem, we're going to use these base equations when we do our left side here. So as we're doing this a dot ds for the top, bottom, and walls, we are going to use these values. Oh, sorry, these values. And then the dv we are going to use for the right side solution. Okay, so moving on to solving the problem. Okay, so to solve our left-hand side, we are going to break up our solution here into the three different surfaces that we have: the top surface, the bottom surface, and the walls. So we're going to go ahead and set up our equations to start out with. So we have our equation A here. I'm going to erase this highlight here. So we have our A, and we are going to multiply that by the ds for our A. So our the ds for this particular surface is the top circle. I'm going to go ahead and paste all of these down here, right? Because we're going to find the differential surface for all of them. So we're going to set all three of them up, and then we're going to solve all three. So for the top, so what is our top here? So let's go up. So we have a circle. So we are going to take the expression for the differential surface for a circle. So surface area for a circular shape, and then we are going to look at the figure and figure out our vector direction for our ds. So we're looking at the top here. So we're looking at this one, and our vector direction that's perpendicular coming straight up is going to be the z hat direction here. Okay, so that's our first ds value. So using the general equation and then looking at the figure to figure out our vector direction. Okay, so same approach for the bottom. We are going to use this same expression here because this is the differential surface for a circle. And then we're going to look at the figure and try to figure out our vector direction for our ds. So it needs to be perpendicular and coming out of the surface that we're looking at. So our surface is here. Coming out of the circle, the surface of that circle is going to be in the negative z direction. So that's what we're going to use here. So we're going to use our negative z direction for our ds vector. Okay, next we're going to look at those walls. So the last piece that we're concerned about is setting up our ds for the walls. So that would be these guys here. So we're going to use the general equation for the differential surface area for the walls of a cylinder. And we're going to copy this guy, and we're going to paste down here. Just take our general expression. Oh, did I copy the right thing? Maybe I didn't. No, I did not, sorry. So I'm going to copy this guy, or maybe this one here. So this one we can actually take our general vector direction, because anytime we set up a cylindrical coordinate system, when we have the walls of a cylinder in that cylindrical coordinate system, our vector is going to point out in the r hat direction. The only reason why I don't want to tell you that this is the general rule for a surface for a circle for the vector is that you may have circles in different configurations, but it's a pretty good general rule for these as well. But just make sure to double check. But for the cylinder here, we're going to have that in the r hat direction because this is going to be normal to our surface and it's pointing out radially in all of our directions here. So at every point in the coordinate system, that r will be perpendicular to that surface. So it's coming out radially kind of at all sides here. Okay, so now we have all of our pieces set up, so let's go ahead and solve. Okay, we're going to start with the first one. Okay, so for the first one, we're going to use our vector rules to cancel some of the things as we dot them. So first off, r hat dot z, because these guys are perpendicular. If you dot two perpendicular vectors with each other, the answer is 0. And then z hat dot z. If you dot two vectors with each other, it's going to be equal to the magnitude of the vector squared. And in this case, when you're dealing with a directional unit vector, that answer is going to be 1. So over here, we can cancel this first. So we can cancel this first r dot z. This term is just going to go to 0. So we're just going to have these two multiplied by each other. So we're going to have 2z z hat multiplied by r dr d phi in the z hat direction. Okay. So we're doing this from the top. So these guys are going to become 1 when we dot them with each other. So we can take them out of the expression. And we are left with, I'm going to pull this 2z to the outside because we don't have a dz. We just have dr and d phi. So I'm going to break up my integrals here, just break up the expression. So I'm going to break up this r dr, and then I'm going to break up this d phi separately, because every differential piece here, these are going to have their own bounds. So this dr is going to have its own bounds, and this d phi is going to have its own bounds. So that's what I want to find next. What are my bounds for r, and what are my bounds for phi? Well, what piece am I looking at for this top piece here? So I'm at the top, right? And I'm at the top, and I want to find my bounds just for this particular piece. So for this piece, what am I looking at for r? Well, r is starting in the center here and then going out to here. So we were given r equals 5 by the problem, so my r is going from 0 to 5. So 0 to 5. And then for my phi, I am starting, right, I'm going all the way around for my phi angle. So I am going to have 0 to 2 pi because it's the full circle. If it was a half circle, it would be like 0 to pi. If it was a quarter circle, it would be 0 to pi over 2. Okay, so now I'm going to evaluate. So 2z, and then I'm going to end up with r squared over 2 from 0 to 5 multiplied by phi. When I integrate that d phi, I'm just going to get phi, and 0 to 2 pi. Okay, so I have a constant for z here because I didn't have a differential. So what is my z at this location where I'm looking at right now, right? So let me look at my shape. Where I am right here, my z is equal to 4. So my height is 4 here. So I'm going to plug in a z equal to 4 for this section of the equation. And then I'm going to go ahead and solve. Okay, so I have 2 times 4 times 5 squared over 2 times 2 pi minus, so I did all of the upper bounds here. Now I'm going to do all of the lower bounds. So 2, 4, so z is the same for both. And then I have 0 squared over 2 times 0. So this piece obviously becomes 0. Oops, this piece 0. So my solution here is equal to 2 times 4 times 5 squared over 2 times 2 pi. And that, just going to use a calculator in the background here to double check my numbers. 2 seconds here. Oops, lost my screen display. Damn. 2 times 4 times. So that is going to be equal to 200 pi. I'm going to come back and double check that in a second here. Okay, so I have 200 pi. All right, so then for my bottom. So similar approach for the bottom. So the only thing that's different in this expression is I have a negative z, right? But I'm going to do the same approach for everything else. So, okay, so first things first, what can I cancel? Well, r dot z, r hat dot z equals 0, because they are two perpendicular vectors dotted with each other. Z dot z, z hat for these two terms here is going to equal 1. So I'm going to cancel this piece out to start, and then I'm going to end up with the integral of 2z z hat multiplied by r dr d phi, or sorry, dot in the z hat, negative z hat. I'm going to pull that negative up front. Okay, so these guys, z hat dot z hat, oh sorry, equals 1. And so that term is going to drop out, and I'm going to end up with 2z r dr d phi, and then I'm going to break up my integrals in the same way that I did before. So I'm going to do negative 2z, and I'm just trying to show all of the steps here. Obviously, I think it's good to see everything from start to finish when you're doing problems for the first time, just to kind of get an understanding for what's important here. Okay, so now we're looking at our bounds. So we're worried about the bottom circle for this problem, right? Bottom circle. or this section of the problem. So our bottom circle here is right here, right? Okay, so what's our phi and what's our r? Because those are what we're have a differential change for, right? We have dr and we have d phi. So our phi is, we've got a full circle, right? 0 to 2 pi again. And then our r just goes from 0 to 5 out here. So that's what we're going to do. So 0 to 5, 0 to 2 pi. And we're going to evaluate this guy. So negative 2z, and then we have r squared over 2 from 0 to 5 multiplied by phi from 0 to 2 pi. So if you kind of looked ahead, you would maybe get a hint for what's going to happen next here. But so our z is, we treat it as constant, right? So our z has a value here, and it's actually equal to 0 because we're looking at what is z where our circle exists, basically. Like what is z at the point where that circle is, and in that plane z is 0. So this whole expression is actually going to cancel, and it's going to go to 0. If you can look at the shape and determine that right away, you can save yourself some trouble with the math, but I think it's good to kind of show everything out so that it makes sense as to why that is the case. Okay, so next we're going to do the walls. So we set up our expression here, and this is our a, and this is our ds. So now we're going to dot these guys and see what we can cancel. So we are going to cancel z hat dot r hat equals 0 because they are perpendicular, and then r hat dot r hat equals 1. Okay, so now we can keep just our r hat terms. So we're going to end up with r squared r hat, right, multiplied by r d v dz in the r hat direction. And these guys, r hat dot r hat, again, equal to 1. So we're going to have r cubed d phi dz. Now we're going to break things up here. So our r, we don't have a dr, so we can treat it like a constant, pull it outside of our expression. So we have r cubed, and then we're going to break up our d phi and our dz into their separate integrals, and we're going to find the bounds for each of them. Okay, so our bounds for phi for the walls. So when we're looking at the walls, they do wrap all the way around the figure. So our phi for the walls, because we've got them up here, they're going to go all the way around, right? All the way around the circle. So our phi goes from 0 to 2 pi, right? 0 to 2 pi. 2 pi radians is 360 degrees, so all the way around. Z is going to go from 0 to 4. So z starts at 0 here, goes all the way up to 4. So that's what we're interested in for these bounds, 0 to 4. Now we are going to evaluate. So we're going to have r cubed times phi, 0 to 2 pi, times z from 0 to 4. Okay, our r here at the walls that we're interested in. So at this location, r is going to be a constant, right? And it's going to be equal to 5. So all around the walls here, right, where this exists, r is going to be equal to 5 in this coordinate system. So r is 5, so we can just plug in our value for r. So we're going to have 5 cubed times 2 pi. So we're looking at the top bounds first here. 5 cubed times 2 pi times 4, right? And then we're going to minus the bottom bounds, 5 cubed times 0 times 0. So this piece is going to cancel, equal 0, right? And so our answer here, 5 cubed times 2 pi times 4 is going to be equal to 1,000 pi. Okay, so our answer here, we have 1,200 pi for our solution. Okay, so for the left side, that's what we got. So next, we're going to do the right side to verify that the two sides are equal. So looking back at the general equation, what we're doing next is we're going to look at this del dot a, then we're going to multiply by the dv, and then figure out the bounds for the volume. Okay, so let's go ahead and just get started with that guy. Okay, for the del dot a, what we're going to do is we're going to use a general equation. With this general equation, you can plug in your values from your cylindrical vector. So this general equation is just for cylindrical coordinates. There is these will be different for the Cartesian, spherical, and cylindrical coordinate systems. This equation is just for the cylindrical coordinate system. So just keep that in mind. I'll throw in a cheat sheet with all of those. You can have on the cheat sheet this del.a pre-solved if you want to save yourself some time and kind of plug in your pieces, but you should know kind of a little bit about where that comes from and how to derive it. So I'll include a video on how to do that. But right now we're just going to plug and play here. Okay, so we're going to grab our A vector. So this is our value for A. And I'm going to show you how you plug this into your expression here. So I have my A, so I'm going to copy this guy. All right, so when I have A, the A is just this general cylindrical vector. These AR terms, A sub R, A sub phi, and A sub z, just mean the magnitude in the R, phi, and z direction. For my vector here, I have magnitude in the A sub R direction and magnitude in the A sub z direction, as we can see by looking over here. But I do not have any magnitude in this A sub phi direction. So I'm going to cross out this phi term, and then I'm going to plug in my values for A sub R and then for A sub z. Then I'm going to solve this equation and figure out what I get from my del operator dot A. So I have 1 over R times the partial derivative with respect to R of R times R squared plus 1 over R, oh, sorry, that one dropped out, plus partial with respect to Z of 2Z. Okay, so quick reminder of partials. When I take a partial, say for example, I have a partial with respect to x of 3x, y, z, right? I only care about this. I only care about the, I'm treating this as the only variable in the expression. Everything else is a constant. So when I evaluate this, this would be 3yz. It's the same as if I were to do like any other constant times x. This would be 4. This yz is essentially treated as a constant, even if it's not in the expression, just because we're taking that as a partial derivative, so we're only concerned with the change with respect to x. Everything else we treat as a constant. If, for example, you have a partial of something, and this number is not in the expression, the answer is going to be 0. It would be the same as if you took the derivative of a constant, just because we are treating these as constants. Okay, just a quick refresher. And let's go and solve our equation. Okay, so one thing we need to keep in mind is that we should do what's inside of the parentheses first. So we're taking the partial derivative of r cubed before we multiply by that 1 over r. Make sure that you always keep that in mind when you're dealing with the del dot A for cylindrical coordinates. This will be a common theme. So 2, and then we have 3r squared times 1 over r. So our del dot A here is going to be equal to 3r plus 2. Okay, now that we have this del dot A, we're going to plug it into our general expression here with our dv, and we're going to find the bounds of our dv expression and then integrate. So not, and then we're going to take this guy, right? So this is our del dot A, and we're simplifying. We always simplify before we integrate, and then we're going to get that dv. So I'm going to take the dv that we introduced before up here, and again, this is a general dv expression for a cylinder, and I'm going to go ahead and use that here. Okay, so we're going to multiply by dv. Notice that dv is not a vector because it does not have direction. So there is no vector term at the end here, and there is no vector sign, which means we're not dealing with a vector here. Okay, so we're going to distribute the one variable that we have before we do this. So we're going to end up with 3r squared plus 2r, okay? And then we have dr, d phi, dz. Okay, now let's break things up here. Okay, so 3r squared plus 2r dr, and then we're going to multiply by the integral of d phi multiplied by the integral of dz. Okay, so now the last thing that we need is our bounds for these three integrals. So we're looking at the range for the entire shape. So we need the range for r for the entire shape and phi and z. So we're looking at the whole cylinder here. So for r goes from 0 to 5 for the whole cylinder. Phi goes from 0 to 2 pi, so full angle, and z goes from 0 to 4. So we're just looking for the height, the full angle, and the radius. So 0 to 5, 0 to 2 pi, 0 to 4. Okay, now we're going to go ahead and solve that. So we're going to end up with, after we integrate, r cubed over 3 times 3 plus r squared over 2 times 2 right? And then from 0 to 5 multiplied, I might move this over a little bit because I'm running out of space here. Multiplied by just phi from 0 to 2 pi, multiplied by z from just 0 to 4. Okay, so we're going to simplify a little bit here. So we just have r cubed plus r squared from 0 to 5, multiplied by phi from 0 to 2 pi, multiplied by z from 0 to 4. Okay, so top bounds minus bottom bounds here. So 5 to the third plus 5 squared for our tops first, times 2 pi times 4 minus, we're plugging in 0, so 0 to the third plus 0 squared times 0 times 0. So the second piece is going to 0. Our answer, as we solve it out here, is going to be 1200 pi. All right, so we found that we solved the, I don't know why I have another copy of this here. So we solved the left-hand side, and for the left-hand side, we got 1200 pi. Then we solved the right-hand side over here, and we saw that after solving the right-hand side, we also got 1200 pi. So in this case, we proved that side 1 was equal to side 2, and therefore we proved our divergence.